Okay, the second way that we can solve our quadratic equations and we can come up with the solution is to use square roots. So remember we talked about it could be called a solution, it could be called a root, or it could be called a zero. Well, we know a solution is the answer to our problem. When we factor, we are setting them equal to 0, so therefore that's why it's called the zeros of it. Now, if we use square roots, they would be the roots of the problem. So once again, we're doing the exact same thing. We're finding the same answers. We're just finding them with a new form. In a lot of equations, all we have is one squared term. We don't have maybe 3 terms. We might just have a squared term and then a constant term. And in that case, we can't use factoring. So when we can't use factoring, we're going to look at the 3 other ways to find solutions for our quadratic when we cannot factor. Roots is the first way. To understand roots and to solve for roots, we have to have an understanding of what a root is. Okay, a square root is simply asking us to find a number that it's multiplied by itself to get the answer. When we are looking at a square root, we have this little squiggly line, and it's called the radical. Okay, it's the radical sign. Your entire part is called the radical, and the number that is actually underneath is called the radicand. Okay, the radicand, every number, every term actually has an exponent. If there is no exponent written there, it is understood to be the number 1. But what's informationally important about this is that it gives us instructions. It's an instruction sheet. The root number that we have listed at the top tells us what we need. Just like in a fraction, we have what we have over what we need. If I had 1/2, this would tell me I need 2 to make a whole. I have 1. So I don't quite have a whole. If I had a pizza and I had it cut in half, I need 2 to make a whole pizza. I have 1 of them. So I have 1/2 of the pizza. For that, our square roots, or our roots and radicals, give us the same exact information. They tell us what we have over what we need to be able to make that whole and get it out. So when we solve for square roots, we are always thinking in those terms of what we have over what we need. Okay, and whenever I often talk about it as escaping jail or getting out from underneath the radical, those ways. So we're going to walk through a couple different ways to understand why it escapes as it does. And then it is just personal preference for you on which way makes more sense for you. So if I had the square root of 2, the important thing to notice is that when we have a square root, in the same way that if I were to write the number 9, my 9 technically has the exponent of 1 on it, but we don't have to write that exponent. In the same way, when we have a square root sign, there is an understood 2, but you will not see the 2 written. It is understood, just as if our exponent of 1 is understood. But in this case, I wrote the 2 so that we could see what we're working at. It's telling me I need 2 of the exact same number to solve this root. I can rewrite 9 as 3 times 3. So it says I need 2. I have 2, so I circle the 2. I circle whatever I need. And then it gets to escape out from underneath the radical. The important thing when you're doing it this way, though, is that it is not escaping as 3 times 3. It is escaping only as the base of what you needed. So in this case, I needed 2 3s. So if I had a set of cards, I would put those 2 3s together and I would set them aside and it would just be a 3. And this is written wrong on there. So it escapes simply as a 3. Another way to rewrite this is to say I have the square root of 3 squared. I could rewrite 3 times 3 as 3 squared. When your root matches your exponent, it erases all of it. And you're simply left with what your base remains. So in that case, you can see why we just have the 3. But it always escapes just as the singular number that you had 2 of. So in the second one, we have the square root of 16. Again, I didn't write the 2. It's an understood 2 in that case. I can rewrite 16 as 2 times 2 times 2 times 2. And then I can tell myself I need sets of 2. I have one set of 2, so he gets to escape. I have another set of 2, so he escapes. The first set of 2 escaped as a 2. The second set of 2 escaped as a 2. Once they're on the outside, they are multiplied together. So I have 2 times 2, and then it's 4. I could have rewritten this as the square root of 2 squared times 2 squared. So my root matches my exponent, so they just go away. My root matches my exponent, so it all just goes away. And all we are left with is 2 times 2, which is equal to 4. I could have also written this as 4 times 4. I have to, the whole thing escapes as a 4. I could have also written it as 2, the square root of 4 squared. My root matches my exponent. When my root matches my exponent, the entire thing goes away, and I'm simply left with the base. Okay. So for square roots, we have rules about square roots in the same way that we have rules for all of our numbers. If I had 3 times 3, I could say 3 times 3 is equal to 9. If I had, I can put them together if I am looking at something where if we have 3 times x times 4 times y, we know that we take like terms, and like terms can be pushed against each other, and then they can also be combined. 12x times y. Roots work the exact same way. We can look at our roots, and as long as the root of our radical here matches. So in this case, this is a square root, so I have a 2, and this is a square root, I have a 2. As long as my radical root matches, then it's considered like terms. And like terms can be combined. So if I have the square root of a times the square root of b, I can combine those just like I combined 3 times 4 into 12. I could combine the square root of 3 times the square root of 4 into the square root of 12. They can be combined. That means that we can also work backwards. We could take the square root of 12, and we could say it's the square root of 3 times the square root of 4. This is convenient to think about because I know that the square root of 4 is the square root of 2 squared. I can rewrite 4 as 2 squared, and so my root and my exponent match. So now I simply have the square root of 3 times a positive 2, which we always put the root at the end, the square root radical at the end, and our whole number at the beginning, so we would have 2 square roots of 3. So while we can combine them, we can also break them apart. They can have different values to be able to do that. Like it can help us a different way. So in the same way that we can do it with multiplication, we can do the same thing with division. We can take something that is inside a radical together, and we can separate the radical. Or we could take a radical that was already separated, and we could combine it back again together. Now, the thing to note is, again, that the radical root must match. We are thinking about this as like terms, like families, in the same way that you cannot take x squared and add it to x and get that to be 2x cubed, or however you would want to do that. They have to stay as two separate terms. These are two separate families. In the same way, when we are looking at a radical, the root determines the family. So in this case, we have a square root, which is an understood 2. If I had a cube root, which would be a 3, I could not take the terms and multiply them together because these cannot be combined. They must stay separate. Okay, so here are some examples. We started with a full radical here, and we broke it up. We can break it up into 4 times 9. We can start with square root of 4 times square root of 2, and we can combine them together into the square root of 8. We could take two separate radicals, one on the top, one on the bottom, and we could put it all over one radical. Or we could take a full fraction that's underneath, and we can separate it into two separate radicals as well. So on this, we have some practice. In this case, however we choose to think about the 24, we can find some perfect squares. If I wanted to look at it through a perfect square, I would say that 24 is the square root of 4 times 6. The square root of 4 is a perfect square, so the square root of it is 2, so I'd have 2 square roots of 6. In this case, separating it into my separate radicals helped me see which part I could simplify. Now here I've got 15 and 6, so I've got 3 times 5 for 15, and I have 2 times 3 for the 6. Well, it would benefit me if I put these together. If I put them together, then I would have 2 3s underneath the same radical, which tells me I need a root of 2. So I would be able to get my 2. So by multiplying 15 times 6, I get 90, which gives me 9 times 10. 9 is that perfect square. It's 3 times 3. I need a set of 2 to be able to pull it out. So my 3 goes on the outside, and my 10 just stays underneath the radical. If I had this as 90, I could go ahead. Another way to think about it is to do 15 times 6 gets me the 90, and then I could break it back apart into the square root of 9 times the square root of 10. And then that way we already see that we've got our square root of 9 is 3. Our square root of 10 can't be simplified anymore, and we have 3 square roots of 10. So for number 3, we have square root of 7 over 16. So whenever I break it apart, I get square root of 7 on the top and square root of 16 on the bottom. This is super convenient because 16 is 4 times 4. It's a perfect square. So I have the square root of 4 squared. So my root and my exponent match. I could also say the square root of 4 times 4. I need 2. I have 2. They escape as a 4. So either way, I have square root of 7 on top and I have 4 on the bottom. So for the fourth one, we could put it back underneath and we could say it's the square root of 7 halves as well. And when we're looking at it, it does not simplify. And this is where we get to talk about rationalizing the denominator. When we rationalize the denominator, there is a special rule. So as we were looking at that square root of 7 over the square root of 2, never, ever, ever can you leave a square root in the bottom of a fraction, ever. It is against the rules. And so the way that we do that is this term, rationalizing the denominator. And from our math rules, we know that we can multiply anything by the number 1 and it never changes it, because the number 1 for multiplication is the identity value. So it allows you to still look at yourself in the mirror and be yourself. And so when we multiply by the number 1, we're not really changing it. It's changing forms, but we are not changing the value of what we have. Now, the number 1 comes in many, many forms. When it comes to a fraction, the number 1 always means, remember as a fraction, it's what you need to make a whole over what you have. And as long as I have all of the pieces needed to make an entire pizza, then I have 1 pizza. So that doesn't matter if I have 10 of 10 slices, 5 of 5 slices, 3 of 3 slices. As long as I have all of what I need, I have the number 1. So that makes it super convenient when we were looking at the fraction involved with our roots. So I'm specifically looking at my denominator. My denominator is my problem, so I want to get rid of my denominator as it is. My square root of 2 says I need 2, and unfortunately the exponent of my 2 is an unwritten 1, so it says I only have 1. Well, if I need 2, but I only have 1, I need to add another 1. I need to add another square root of 2 to this. I need to get another 2 underneath the radical. Well, I can't get another 2 under the radical by adding it. I have to get another 2 underneath that radical because, remember, we just learned that a times square root of a times the square root of b gets us the square root of ab. That's how they both get underneath the radical. So I need to multiply by something. I need to multiply by that other 2 to get it underneath the radical. One of the important things to note is that anytime you square a square root, you get the number itself. And that's simply because if I had square root of 2 and I square it, that means I now have square root of 2 times the square root of 2, from which we know is the square root of 2 times 2, all underneath the same radical. So I need 2, I have 2, I simply have, in this case, the number 2. So we're going to square our square roots by choosing the value of 1 to be exactly what the denominator is. So in this case, the denominator is the square root of 2. So I'm going to multiply by the square root of 2 over the square root of 2, which is really just the number 1. So on the top, I now have square root of 3 times the square root of 2. On the bottom, I have square root of 2 times the square root of 2. So whenever I use my rule, I can combine these. I have square root of 6 on the top. On the bottom, I now have the square root of 2 times 2. I need 2. I have 2. It can also be written 2 squared. I need 2. I have 2. My root and my exponent match. I simply have a 2. So now we have rewritten square root of 3 over the square root of 2 can be rewritten. It is equal to the square root of 6 over 2, the number 2. So again, I have not changed anything. I didn't change the value of it. We just changed what it looked like. So where do the roots come from in the first place? We've always heard of PEMDAS. When we change it to PERMDAS, it helps our brains make sense because everything has an opposite. Good has the opposite of evil. In this world, you know, every superhero has a villain. In math, all of the ways that we work with our problems always have an opposite. So addition has the opposite of subtraction. Multiplication has the opposite of division. Exponents, which we know, as in this case, like x squared, would have the opposite of a root. So the opposite of an exponent is a root. When you take the square root of an exponent, they cancel each other out. When you have a root and you use an exponent, it cancels it out. In the same way that multiplication and division cancel themselves out, addition and subtraction cancel themselves out, exponents and roots work back and forth to cancel out. Okay, so how do we use all this brand new information about roots to help us find a solution for a quadratic? Well, often in a quadratic, you may only have one squared term. So we can't factor this. If I take 2x squared minus 1 equals 17, I can't factor it. So I can't use that. We haven't learned our other forms yet, but I can say, hey, all I have is one term. I know how to get that term by itself. So we go all the way back to the very beginning. And my silly story of X wants to go to the movies by himself. How do we get there? Well, he's already all gathered together. We've got all of his parts together. So who do we get rid of first? We get rid of our external numbers, our external terms. So we're going to get rid of our 1. We're going to simply subtract 1 from one side, subtract it from the other side. So now I have 2x squared equals 16. Now we get the monkey off his back. I can divide by my coefficient of 2, divide by my coefficient of 2. So now we are left with x squared equals 8. So since I have to do the opposite, so in all the cases, in this case, the opposite of addition was subtraction. In this case, the opposite of multiplication was our division. I now have an exponent, so the opposite is the root. I need to take the square root of both sides. The important thing to note when we are taking square roots is that this x term was squared from the very beginning. When we got our equation given to us, the x term was already squared. The constant terms were not squared from the very beginning. So every time we take the root of a number that was not squared in the first place, we have to add plus or minus. We have to add 2 signs. And a great example for this is if I replace my term of x squared, if I replace it as a 9, okay, and I'm asking myself, what 2 numbers can multiply together to be 9? I can have the solution of 3 times 3 can be multiplied to be 9. I can also have the solution of -3 times -3 can also give me the answer of 9. So when we are taking the square root of a number, in this case, like the number 9, I can get there 2 different ways. So that is the reason why when we take the square root of a number that was not already squared, we must add both plus or minus. We can have the positive versions can get us there, and the negative versions can also get us to the same answer. So in this case, when we take the square root of both sides, the square root of x squared, we know when the root matches the exponent, it's simply the base. So all I have is the x. In this case, the square root of 8 is the square root of 2 times 2 times 2. I need 2. I have 2, so I can circle the 2 that I have as a set, and it escapes as a 2. But I have 1 that stays left over underneath the radical. So I would have x equals plus or minus 2 square roots of 2. Another way that we could have done the square root of 8 is we could divided it up into the square root of 4 times the square root of 2. The square root of 4 is 2 squared. So that gets us to the need to have 2, my exponent and my root match, and I simply have that 2. And then I have the square root of 2 left over in that case. Okay, so for this example, we are starting out with 1/3 times x plus 5 squared equals 7. So again, I'm going to go all the way back to PEMDAS. What do I want to do? I want to get x by itself. Who do I get rid of first? I'm going to get rid of my coefficient, my 1/3. I'm going to use the opposite, the inverse of it. So I'm going to multiply by 3. What you do to one side, you do the other. I multiply the other side by 3 as well. So I'm simply left with x plus 5 squared equals 21. Now, one of the things that is quick in this case to say, oh, I know what to do with a binomial squared. I use FOIL. So I'll just FOIL this out, and I'll get x squared plus 10x plus 25 equals 21. Well, that's great, but now you have given yourself 2 terms in 2 different families. So you have not simplified your problem. You've just made the problem more difficult. Our goal is to not make the problems more difficult, is to always be working towards a solution and making this a lot easier. So instead of looking at x plus 5 squared equals 21, what if we looked at this as a squared equals 21. If we replaced our entire x plus 5 with one variable, if I had a squared equals 21, I know that I could simply take the square root of both sides. So that's what we're going to do. We're going to take the square root of our entire left side, take the square root of our entire right side. Well, I have 2 of this entire binomial, so my base happens to be the entire binomial that gets to stay. Now, over here, I just took the square root of a number that wasn't squared in the first place. So we add plus or minus, and we leave our square root of 21. Now, I go back to ask my question again. X wants to go to the movies by himself. Who do I need to get rid of? He has a positive 5 attached to him. I'm going to subtract the 5 from both sides. So x plus 5 minus 5 leaves me only x on that side. Now, the rule on this side is, remember, we can only add and subtract like families. Well, my negative 5 here is not a root. It is one family. It might be this green family. My square root of 21 is a root. It is a completely separate family. They cannot be joined underneath together. This is not negative 5 and 21 and getting us 16 as an answer. We have one family that is an integer here. We have another family that is an irrational number with a square root of 21. So we cannot combine them. They don't get to live in the same circle. So we're going to keep them separate, and we're going to put our negative 5 first. We leave our plus or minus, and we write the square root of 21 on it. Now, this is a perfectly acceptable answer. You can leave it as negative 5 plus or minus the square root of 21. What it really means, written out, is that you have 2 solutions. You have x is negative 5 plus 21, and x is negative 5 minus square root of 21. So we have 2 separate solutions. It can be written all together as one individual solution. So one of the things that we get to ask ourselves then is, what happens when that number, when the radicand, the number underneath the radical, is negative? Well, that poses a problem, because as we learned at the very beginning when we were talking about real numbers and rational and irrational numbers, is that when we ended up with that negative sign, we end up with things that are irrational and imaginary. So we're adding a whole new term in there. The thing that we can look at when the number is negative is we can use that rule that anything that is multiplied can be both combined and it can be re-separated. So I can separate my square root of negative 4 into square root of 4 times the square root of negative 1. Square root of 4 is something that I can solve for. I can say that's 2. The square root of negative 1 is a special term called I. And we will do a whole lesson on I. Right now, you just need to know that the square root of negative 1 needs to be rewritten as the value I. And then there's lots of things that we can do with I from that point forward.